everyone. Today we are here to introduce our latest manipulator, which is the WidowX AI. It is the first in many that are coming out this year, and it is designed specifically for the AI and machine learning community. I am Matt. I am the founder of the company, chief nerd and chief mechanical engineer.
I'm Luke. I'm the lead software engineer here at Trossen Robotics. I make all the software that goes on the robots.
And I'm Shantanu. I'm the machine learning evangelist at Trossen Robotics.
And you take care of the pipelines and everything after the fact, and interface our arms and our software with all of the software that the other companies are out there making. So all of this kicked off about a year ago when Stanford released their first Aloha kit using our legacy arms back, I want to say it was December 6th, but it was sometime in December. Actually, if not last year, it's 2 years ago now. So it's all the way back in 23. I still forget we're already in 25. And that kicked off like an entire new industry and research. I mean, it's not like it wasn't there before, it was already there, but that was just kind of like a tipping point where they nailed it with sort of a form factor and a design and a layout that just worked for everybody. And overnight, we just had an unbelievable amount of interest in the kits. We were very happy and proud they chose some of our legacy actuators, and it has just done nothing but take off since then. So if you're anywhere in the machine learning or AI community, you've probably seen the Aloha project, probably seen the stuff that's coming out of it, seen all of the other companies and research labs that have started mimicking that work and doing their own. It's unbelievable how fast this stuff is moving. You know, I've often said that robotics is a combination of two of mankind's greatest inventions. And the first one being the industrial age, where we learned to automate physical labor. And the second is when we had started with the information age with computers that's now culminating with AI, which is basically automating intellectual labor. And robotics is basically the combination of those two things together. Our old legacy arms were built on old Dynamixel actuators that were great for their time, but there's new types of actuators that have come out, and we're starting to build new manipulators for those. Each of us is going to go over our different areas of the arm. So I do the mechanics, Luke's going to go over the software, and Shantanu is going to go over the pipeline. So for my area, I worked with the team to do the design on these arms, and so we'll go over some of the features and decisions we made on that. To start with, this is using new types of servos. They're called QDD servos. That stands for quasi-direct drive. Basically what that means is that they're low gear. I guess it kind of means it's a 1 to 10 ratio or lower, and that gives you a few features. It's efficient back drivability, so it's not too hard to move it when you're driving back. Two reasons for that when it comes to machine learning. One is you have a leader arm that a human's moving and you want it to be pliable and easy to move. Second is when you're doing machine learning and it's hitting resistance and things of that nature, you want that to be kind of as loose and smooth as possible so that the sensors are seeing that. You don't have a bunch of gear trains in there getting in the way.
And also, if you happen to run into something like a table or a workpiece, it does not damage the motor.
Basically, it's a high torque motor that's in a lighter package that's easier to work with, and they've got 2 encoders inside. So all of our new arms have that in there, and we have a 6th-off arm here with 7 servos total, 6 for the arm and 1 for the gripper. The layout of the arm was designed by choice because a lot of our clients said, can you keep it in a format that's popular, that there's a lot of data sets out there for already? And so this certain layout here has, with a lot of popular arms use this. And so on our first one, we didn't want to go astray and completely redesign the arm because people are working with data sets that they've already built models on. So we're going to expand to some different layouts in the future. This is kind of a standard, and that's why we chose this one. Like one of the things that's on here is your roll, pitch, and yaw of the wrist is kind of separated. And now on more modern versions of arms, people are trying to do different layouts that allow it to all pivot in one point, and our next models will have that as well. But we stuck with the standard to come out of the gate. Some of the other features we have on here is an all-metal design with idlers on the first 3 joints. So we have them down here in the shoulder, in the elbow, and in the wrist, and that's for stability. Because when an arm is quickly moving around, you need to have idlers on both sides. You have a horn on one side and an idler on the other side for that. At the end where you have less inertia, you don't need them as much, and so you'd actually be making it worse by having extra weight. So you just go down to being connected to the horn on those. So we also do cable runs through our idlers, and we do that because that keeps the cables out of the way, so you're not catching them on things. Looks nicer, but the biggest feature is that the cables last longer because they're going through a center rotation point rather than rubbing around other parts of the arms. The only place we couldn't get away with it is the one you see sticking up here. We wanted to run it through this joint, but we didn't have enough room by sticking with the standard, so we had to keep it up there. We have bumpers on the front here. So we had a client tell us that they keep scraping things. They keep hitting stuff with the metal bar on the gripper here. And so you don't want to be like trashing your refrigerator when you're reaching in and grabbing stuff. So it was actually suggested by a customer. We said, good idea. Rubber bumpers here. We also have rubber fingertips on the end. The fingertips can be replaceable, so you can pull your fingers off and it doesn't, like, the whole gripper doesn't fall apart because like your rail isn't attached to that. It's attached to the carriages. On the inside here, we've got a rack and pinion, all metal, very low to no slop on them. And then what you don't see on this model that's coming on the, I shouldn't even say the next model, but on the next series of these, is we're putting little bearings in here that'll press on the rails to also make sure that they don't get loose. We have 16 mounting holes on the front, so you can have different cameras and sensors mounted on. You can see this has got the camera. You mount the handles for the leader arms underneath down here, so we have a lot of different mounting points. And then we have mounting points all along the arm for cable runs. So we don't have the cable on here for the camera at the moment, but when you have a camera on a follower, you've got a big cable that runs along here, so we've done cable management for that as well. Last but not least is we spent a little time doing some styling on this. We tried to make it look nice and not boring, so it stands out a little bit. That also gives you a little bit more features when you're doing training on a model so that it can see those. We have historically had pretty ugly arms because we've used extruded aluminum on our legacy arms.
Holy Jesus! What is that?
And so we wanted to step our game up and put a little bit more effort in that. This arm is currently all CNC'd metal. It is very tough, it is very rigid, and that's what we did in the first model. But we want to keep getting our costs down, and so we're looking to injection molding for this, where these big sections will move to injection molded plastic, but it'll be just as rigid, keep the styling, but start driving the cost down so that we can pass that along to customers and keep making these as cheap as possible, because basically all of our clients and customers are saying that cost is very important, so we're very aware of that. The price point of this arm right now is as aggressive as we can get. But we understand that basically arms are moving towards being like appliances, and so we have to move towards manufacturing methods the way appliances are made. Well, appliances in your home aren't made out of CNC metal. They're made out of stamped metal, and then you have injection molded plastic shells that go around them, and that keeps your cost way down while keeping your rigidity in place. So now that these arms are going to start going on robots that are basically learning how to do things around the house or clean a hotel room or take out your garbage and things of that nature, they have to start becoming more like a vacuum cleaner. So it's got to get manufactured the same way. So that eventually it's like you buy this, and who knows when we're going to reach that stage where you can buy it off the shelf like a toaster. But we know we're headed in that direction with this stuff. And so the manufacturing methods of these arms is slowly moving in that direction. So that's all the hardware on here. Luke, do you want to talk about the controller that we made especially for this arm and all the features that this involves?
Yeah, I could talk about all of the software that we have going on in this arm. So I guess we'll go to the controller in a second, but the first thing I want to talk about are the controllers inside of each of the motors. So inside of these motors, we use a special control scheme. We call it like extended position velocity mode, where we have a position loop, a velocity loop, and then a feed forward torque option. So using this special extended position velocity mode, we are able to command all different modes using the same operating mode. So those operating modes inside of the controller box, those are idle, which is kind of like a braked, damped, safe mode. So there the arm will hold its current position and try to achieve zero velocity, and then the fingers on the gripper will close slowly. It's very safe. We also have position mode, where you just command positions to all of the joints, along with optional feed forward velocity and accelerations. We have velocity operating mode, which you command velocities to the joints, as well as optional feed forward acceleration. And then we have external effort mode. On the controller, we run inverse dynamics, where we compensate for the forces of gravity as well as joint frictions. These are to keep the leader arms. Whenever you're doing teleoperation, you want the arms to be as lightweight as possible. You don't want to be holding these very heavy arms for long periods of time. So that allows you to control them a lot easier, push them around very easily. Between the controller and the arm, we are using CAN FD, the Flexible Data Rate CAN Bus Protocol. between the controller and the user PC, we are using UDP over Ethernet. So we have these nice ports on the back here. They uses M12X coded to RJ45 to plug directly into your laptop. Additionally, if you are using something like the stationary AI or the mobile AI where you have multiple arms, you can connect them all into a single network switch, just be able to talk to them all at once. You assign different IP addresses to each of the arms that are on the same network segment.
Yeah, we're very anti-USB here.
We are very anti-USB. We like locking connectors here, so you can see that everything is screw-on here, and then we have the locking RJ45 on the user PC.
Yeah, and doesn't that bring extra benefits too? So like if you have a bunch of them set up for like a data collection center, everything's on the network versus being on USB.
Right, yeah, you can route everything to a single server, so if you have multiple of these data collection pods, instead of having everything on one PC and then sending it up to the cloud or something, you can send it back to some like edge computer or service like that. And finally, we get to how the users will actually interact with the ARMs, which is through the lib Trossen ARM C++ driver, the Python bindings in the form of the Trossen ARM package, which is available on PyPI, and the ROS2 Trossen ARM ROS packages. We provide description packages with URDFs and detailed mesh and inertials, the MoveIt configurations, as well as a ROS2 hardware interface.
So let's speak to the importance of why we offer so many different ways to get into the API and operate the ARM. Because what happens when anytime there's new technology that comes out there is you have early adopters that are willing to go the extra mile to make it work, right? They might write their own drivers, they might, work on buggy drivers, add features themselves. In machine learning research or anything with manipulators for a decade now, that's been going on. What we like to specialize in here is called crossing the chasm. So there's a philosophy that the technology adoption curve basically goes up, and then there's a big chasm from early adopters to mainstream early adopters, where you have to do a lot of work to make it friendly so that your average user can use it. And that's something we specialize here at Trossen Robotics. It's something we've done for 20 years. We take bleeding edge tech, whether it's motors or drivers or controllers, and sew it all together and make it kind of work seamlessly and give demo packages so that if you're a developer, a programmer, you want to buy a piece of hardware and get up and running as fast as you can. There's nothing worse in this world than sitting down and wanting to do something really fun all day or all night and then screwing around doing plumbing work and trying to get a driver working or something like that. It's extremely frustrating. So there are other ARMs out there that just give you a dongle, and it's basically just CAN bus to USB, and you're on your own basically at that point. The whole reason that we've put a ton of work into our controllers, our code, our APIs is so you don't have to deal with that as a developer. All of our kits work out of the box. We have demo code. Shantanu is going to talk about how they're even sewed into the pipelines that are out there. So Luke's team has put a ton of effort into putting all of that onto our controllers. This is a big deal here. This box is almost more important than this ARM. You can buy other ARMs like this in the market. Frankly, you can get them a little bit cheaper because they come from overseas and they get dumped into America. Ours has all of this support around it, and that is what we bring to the table. It's what we concentrate, and that hopefully sets us a little bit apart as a company. One of the other things I want to mention too is, we paid attention to the connectors on these boxes. We wanted them to be more kind of industrial so that things don't fall apart. And there's just one connector for everything. But future versions of this, we're going to have so the e-stops, which we've had people ask about, that's coming on the next version of this so that you can put e-stops wherever you want, plug them into the box.
Right.
We want to put a little screen on it. I'm really excited because I want a little LCD screen that'll give you some readout.
Yeah, right now we just have this LED indicator right here, which will indicate some simple state information, like what operating mode are we in, is there an error, is there a hardware error, things like that.
Super basic.
Yeah. The screen will do a little bit more, like indicating maybe what IP address it's on in case you lose it, or more detailed error information.
Yeah, right now it kind of looks like that box from the old sci-fi show, Twilight Zone, where the guy shows up and he gives you a box and he says you got to push a button on it. And they don't know what happens. And then he goes, somewhere in the world someone dies, but you get $1 million. And he goes, well, what happens next? We take the box to someone else and we ask him the same question. And the guy's face goes blank. Anyway, this reminds me of that.
So we've made a bunch of tools. We have the Trossen ARM driver, we have our integration with Robot, a couple of other tools available to our users. How do they use those tools to create their own machine learning model?
So to begin with, you can collect episodes using the Trossen ARM driver integrated with the Lirobot pipeline, which allows you to collect episodes in the Lirobot dataset format, which is a highly compressed and good quality dataset format that lets you publish your datasets onto the hub. The best part about this dataset format is that it requires a very small space compared to other dataset formats that are available. This allows you to collect datasets in less than a few kilobytes.
Compared to the legacy Aloha kits, which use the HDF5 format, this is significantly smaller, significantly more efficient.
All these visualization tools help you to debug your episodes early on. Like, let's say you have any problems in the camera feed, or there is an overshoot in the joint states. You can remove those episodes and only use high quality data for training your robot.
We talked about parsing the data sets that you have collected to get good high quality episodes. What is the next step in creating your own machine learning model?
Once we collect all our dataset, we can go ahead and train the robot using one of the state-of-the-art models like ACT, Pi0, or Diffusion, etc. The good part is, all these models are readily available on the Lirobot repository.
Yeah, one of the reasons we chose the Lirobot to integrate into our system is that it makes it plug and play with different models and different data sets, isn't that right?
Yes. Let's say I've collected a dataset for picking up a block. I can use that dataset to train on ACT, Pi0, or Diffusion and benchmark my results, and then I don't have to recreate a new dataset or a new format for collecting the episodes. So one single format, you get multiple different models that you can train on, you can benchmark them, and then you can feed forward that thing into your next research. Use the same benchmarkings and results, and then build upon that to create your own policy for training the robot.
Basically to be more efficient, right?
Yeah.
So like, because we have the ecosystem, because it's all tied together for you and those tools are all there in one package, everything's more efficient. Basically you can be up and running and we can be innovating instead of screwing around trying to set things up.
Yeah.
And that's what you get when you buy an ARM. You don't just buy the hardware, you're buying into an entire package, an entire system that already works for data collection, model evaluation, model training, model testing. It's all one package. So not only do we have the ARM, but we also have the stationary kit and the mobile kit, which we'll talk about in another video, but we have entire hardware packages that go with the software packages so that you have a total package to get up and running faster. I want to talk for a second about simulation. So we haven't released any of it yet, but you guys are working hard on it. Can you tell them a little bit about what's coming next?
Yeah, so we're targeting 3 different simulation environments. The first one is the MujoCo simulator from Google DeepMind. Could you talk about how we plan on integrating with MujoCo?
So the MujoCo simulator allows us to create XML files using the URDF that are existing. These give you very high fidelity, highly precise mass and inertia properties that can be used to simulate robots in an environment. And we use DM control, that is a control suite from Google DeepMind again. This allows us to collect episodes using the simulation itself. So you don't have to go and collect episodes using a real robot. You can also train your robot in a simulation and evaluate it so that you don't damage the real robot in case. Once you are done with your training and evaluation and you are satisfied with your results, you can directly transfer all those results onto a real robot without any problem, because all the inertias and masses are exactly precise.
Yeah, we joke about making a commercial where I stand in front of the ARM and say, I'm Matt Trossen, I don't want you to buy my hardware. I'd rather you simulate it first, then come back and buy it. Because that's what it allows people to do, right? It's like having hundreds or thousands of ARMs in simulation, and you don't need as many in real life.
Absolutely. That is also one of the benefits of the second simulator that we're planning on integrating with, which is NVIDIA's Isaac Sim and Isaac Lab, where you can offload simulation processes to your GPU to do thousands in parallel. And then finally, the last one that we are going to integrate with is the new Gazebo Ignition, and tightly integrated into our ROS2 packages.
Yeah, so again, we want modularity, we want choices, right? So we want to release all 3. Those are coming this spring or this summer, so that you can simulate however you like, use whatever data models you like, use whatever storage methods you want. We're all about flexibility here and giving people as many options as they can so they can be up and running. Thanks for watching today. Look out for our next video, which is going to be about the stationary kit itself, and after that the mobile, which are complete kits that use the WidowX AI ARM. We'll see you next time.
Trossen Robotics, helping innovators innovate.